Hi everyone. Thank you very much for the invitation. Today I want to talk about centralizers in automorphism of free groups and group action on trees. And I want to say all that I will say is about a joint work with Sam Hughes and Luis Sanchez Saldana. So first, I will fix an integer n, and I will consider fn to be free group of rank n. So let me just recall what does that mean. So if you fix an alphabet x1 up to xn, so an alphabet with n elements, the free group of rank n will be the set of all concatenation of letters with to xak, where might be plus or minus 1. So you look at all words in the alphabet x1 up to xn, where you can, the only simplification that you can do is simplify x1, xi, and xi minus 1 to be the empty words. And the operation that you have is the concatenation. So this is a universal group because every finitely generated group is a quotient of a free group. And I am interested in the group OTFN, which is the group of automorphism of Fn, which is the group of all bijective homomorphism from the group Fn to itself. So why are we interested in the group OTFN? It's because of the following fact, that since the group Fn is universal, it has a lot of symmetries. So one can easily construct a lot of automorphism of the free group, and the OTFN has a rich family of subgroups. So let me explain how to easily construct automorphisms of free groups. Well, the first example I have in mind is through permutations. So if you take a permutation sigma of the alphabet x1 to xn onto itself, so it's a bijection of the set x1, x2 up to xn. Then you can extend sigma into an automorphism of the free group as follows. So Fn is generated by the set x1 to xn, and you just send xi to sigma xi, and you extend to the set of all words of the free group using, if you take a word w, which is xi1 up to xin, then sigma at of w will be sigma xi1 up to sigma xia. You can easily check that it is an automorphism of the free group, namely that it satisfies the rule of the homomorphism rule and that it is bijective. This is because we take a bijection of the set x1 up to xn. So as you can see, this construction is quite similar to the standard representation of the symmetric group. And in fact, my second example of automorphism of a free group will be matrices with integer coefficients, invertible matrices with integral coefficients. So the construction will be similar, and I will explain in an example. So if you take the matrix 1, 0, 1, 1, and you look at the group Z2 generated by A and B, you can see this matrix as an automorphism of the free abelian group of rank 2. And you can also look at the free group of rank 2 generated by the set A and B. Now, what does the matrix M do to the free abelian group? It sends A to A, and it sends B to A plus B. But we can do a similar construction for the free group. So namely, you can look at the automorphism, which sends A to A and B to AB. Then this automorphism, it's an automorphism of the free group. It is just constructed as a matrix. And in fact, if you look at the action of phi m onto the abelianization of the free group, so you quotient by the commutator subgroup. So this group is isomorphic to Z2. And in fact, the action of phi m at is exactly m. And in fact, you have a surjective homomorphism from the automorphism of Fn onto G ln Z. So in fact, you can see any matrix as an automorphism of a free group. So you can very easily construct automorphism. So now a third example comes from sequences of words. And I will consider as an example the Fibonacci sequence. So consider as above the set A and B, still considered as an alphabet, and I look at the following sequence. So S0 will be equal to A, S1 is equal to AB, and more generally, the nth element of the sequence will be equal to Sn minus 1, Sn minus 2. So it is just a Fibonacci sequence in the language of alphabets. And as before, you can construct an automorphism out of this sequence as follows. So you can consider the automorphism of F2, still generated by A and B, defined as follows. It sends A to AB, and it sends B to A. So why it is linked with the above sequence? It's because for every n, if you look at the nth iterate of A, it will be equal to Sn. So not every sequence of words define an automorphism, but every, in some sense, invertible sequence defined an automorphism of the free group. So there, you can study dynamics of sequences using automorphism of free groups. And finally, I have a more geometric example of a construction of a free group, which is a homeomorphism of a surface. So if you take sigma to be a compact hyperbolic surface and connected surface, and I will fix a base point, and I will also assume that sigma has exactly one boundary component, has exactly one boundary component. So the picture that you need to have in mind is the following one. So this is my surface sigma, and I will take as a base point an element of the boundary component. So since it has a boundary component, the fundamental group of the surface is isomorphic to a free group of rank, say, n. And this is why any homeomorphism of sigma fixing x defines an automorphism sigma x, which is just Fn. So you see that up to homotopy, any homeomorphism of sigma defines an automorphism of the free group. So, and if you don't want to work up to homotopy, homeomorphism in general won't define the automorphism of the free group, but it will define an outer automorphism. Oh. So, definition. The outer automorphism group of Fn, it is the group denoted by out Fn, which is the quotient of the group of automorphism of the free group by its normal subgroup, which are all the global conjugation by an element of the free group. H is in Fn. In that case, if you look at my surface sigma, any homeomorphism of sigma defines an element of out Fn. So you see that what you lose when you quotient by this normal subgroup, namely that you don't now out Fn does not act on Fn, on the elements of Fn, but on the conjugacy classes of elements of Fn. You obtain, you'll gain that every homeomorphism of sigma defines an element of out Fn, so that you can forget about the choice of a base point and you can forget about homotopies of the surface. So in general, we do back and forth. We will use both out Fn and out Fn when studying some algebraic question. So here are the main motivations for studying automorphisms of free groups and outer automorphism of free groups, because they define a lot of distinct, they can appear in a lot of several cases. And now the question I studied is the following: how to understand the group out Fn or out Fn. This is a general question, and we'll follow to understand these groups, we'll follow the problems which are due to Den in 1911. He proposed 3 problems to understand an infinite finitely presented group. So the first one, we will not be concerned about it. It is the isomorphism problem, which is given a class of groups, find an algorithm to say if 2 such groups in the family are isomorphic. The second one is a word problem. Meaning, if you take an element of a given, find an algorithm which gives, if you take as input an element of a given group, says that it is if it represents the trivial group or not. So this problem is solvable for out and out Fn. And the remaining problem that is not known is the conjugacy problem, which is the following: find an algorithm which takes as input two elements T. So I will write it for out Fn. 2 elements of out Fn, and gives an output says yes or no for the following question: does there exist an element theta in out Fn such that theta phi theta minus 1 is equal to psi? So this problem is quite algorithmic, and I studied a linked problem, but a more algebraic one, which is the question of the centralizer. My question was to understand the subgroup T of phi, which is the set of all elements theta in out Fn, such that theta phi theta minus 1 is equal to phi. So you see that this is kind of a dual problem as the conjugacy problem because you look at the stabilizer of the conjugation action of OTFN on itself. And in fact, in general, we use quite similar arguments to understand both the centralizer of an element and the conjugacy problem in a group. I will give as an example the following case of GLNC, which is the group of all automorphism of the C vector space of rank n. So if you take a matrix in GLNC, it has a canonical form, which is its Jordan normal form. That is, there exists a matrix P in GLNC such that the conjugation of M by P gives a block diagonal matrix J, J lambda M, such that each block is exactly the matrix where the upper triangular matrix with lambda I on the diagonal and either 0 or 1 just above the diagonal. Or 0, 0. So in fact, this Jordan normal form completely characterizes the conjugacy class of M, and you can use this Jordan normal form to solve the conjugacy problem in GLNC. But you can also, with this normal form, understand the centralizer of M, because in fact, the centralizer of M will be isomorphic up to permutation of the Jordan blocks. Of the J lambda I. So you can permute isomorphic Jordan blocks, but otherwise the centralizer will be isomorphic to the direct product of the centralizer of each block. And the centralizer of each block is really easy to understand. If it's a homothétie, it is the whole GLNC, or if it's not, then it is isomorphic to the group generated by sum of powers of the Jordan block. So our goal with Sam Hughes and Luis Sanchez Saldana was to construct the objective was to construct such a canonical decomposition for an element for an automorphism of the free group. And in fact, our construction also works for outer automorphisms. So our goal was to construct a decomposition which is quite similar to the Jordan normal form for matrices, but in a non-commutative case, and in fact in a hyperbolic case. So So we first started to try to construct what could be a canonical decomposition of a free group. And the first example that comes to mind, it's not the right one. The first candidate will be to construct a canonical decomposition out of three products of Fn. So a definition, a free factor of Fn, it is a subgroup A of Fn such that there exists a subgroup B of Fn with Fn is equal to the free product of A and B. It means the following. So Fn is generated by A and B, and moreover, if you take any sequence of elements in A and any sequence of elements in B, if you look at the word of the free group, which is equal to A1, B1, A2, B2, you do the same. So it's an alternate product of AI and BI. And if this product is equal to the trivial element, then this means that for every I, AI and is equal to BI is equal to 1. So this means that there is no cancellation and no identification between words in A and words in B. And free product is just a decomposition as above. So here's an example of a free product decomposition. So if you look at F2 generated by A and B, then F2 can also write it as a free product of the group generated by A and the group generated by B. And a non-example in this case will be a power of A, for example. It is not a free product of, it is not a free factor of Fn because otherwise you cannot find the elements, find a group such that the free product of A square and this group generates Fn without having identification, because you need to find, in some sense, the element A. So the first question is, can you find as in so Jordan, for the Jordan decomposition for matrices, you have a canonical decomposition of the the C vector space of rank n. And the question is, can you find for a given automorphism of the free group a canonical free product decomposition? So a decomposition of the free group into three factors, which are all invariant by the automorphism phi. Unfortunately, the answer is no. There exists, in fact, automorphism of the free group such that no power of phi preserves a free product decomposition, and it's even worse. So, and you have an even worse situation because they does not preserve even the conjugacy class of a free factor up to conjugacy. So there exists some automorphism of the free group such that no free factor, the conjugacy class of no free factor is preserved by phi. And one example is the Fibonacci automorphism that I described earlier. Fibonacci automorphism. Phi, which sends, I recall, A to AB, A to AB, and B to A. This automorphism does not preserve the conjugacy class of any free factor of Fn. So our first candidate for canonical decomposition of the free group is not the right one, but it is very close to the right one. And in fact, our second candidate will be action on trees. Definition. Fn tree it is a tree T, so it is a graph, a connected graph with no non-trivial cycles. So it means it's a graph which is connected and simply connected, equipped with an action of Fn by homeomorphisms. So stated otherwise, it's also, you can also look at an Fn tree as a couple T and ρ, where T is your given tree, and ρ is a homomorphism from the free group to the group of homeomorphism of the tree. In general, the tree that we will consider are infinite and even locally infinite. And In fact, these trees generalize the free product decomposition that I explained earlier because of the following example of an FN tree. So I will construct a tree out of a free product decomposition of Fn into A and the free product of A and B as follows. So you start with an edge where vertices are labeled by A and B. And you look at, and you will add edges adjacent to the vertex labeled by A by vertices which are labeled by B1A, B1 minus 1, B2A, B2 minus 1. And you do the same thing, BN, A, Bn minus 1, where all the Bi's are in B. So you look at all the conjugates of A by elements of B. And similarly, you can do the same thing for you add edges adjacent to the vertex labeled by B, by where the other endpoint is labeled by groups of the form A1B, A1 minus 1, AN, B, AN minus 1, where all the AIs are in A. And you can do the same procedure for every vertices. So this gives you an infinite and locally infinite. So the degree of every vertex is infinite. And the interesting fact is that since Fn is the free product of A and B, then the graph that you obtain with this procedure is a tree. The graph is a tree. This construction is due to Serre, Bass and Serre, and it is therefore called the Bass-Serre tree. Associated with A and B. So now we have a tree, and the action of Fn on this tree is defined as follows. So if you take a vertex V, which is labeled by, so if first you take an element G of Fn, and you look at a vertex V, which is labeled by, say, sorry. Labeled by H, A, H minus 1. So I did not mention that, but every vertex has a label which is of the form H, A, H minus 1 or H, B, H minus 1. So you cover the conjugates of every group, the conjugate, you cover the conjugacy class of A and B. And then the action of GV will be the vertex W, whose label is D, H, A, H minus 1, G minus 1. So you just conjugate by G. And you do the same thing for vertices which are labeled by H, B, H minus 1. And this gives you an action of Fn on the Basser tree, where the stabilizers are of a vertex is either H is of the form HA, H minus 1 or HB H minus 1, and the stabilizer of an edge is trivial. So this is why group action on trees generalizes free product decomposition. Now, haute Fn acts on the set of all Fn trees as follows. So if you take phi an automorphism of Fn, and if you take an Fn tree T, so a couple T and rho, the action of phi on the couple phi rho will be just, so you have the same topological tree T, and you precompose the action of rho by phi minus 1. So you obtain an action of haute Fn on the set of all Fn trees. For instance, if you look at TAB, so the tree associated with TA and TB, so I will just write the edge AB. And if you take an automorphism of Fn, so the action that I described above, phi of TAB, phi will send TAB to T phi A phi B. So you obtain the same action as on the set of all three factors. Now, what we proved with Sam and Luis is the following theorem. You take any automorphism of infinite order, and which is not a global conjugation, by an element of Fn, then there exists an Fn tree T rho, which is fixed by the centralizer of phi. So in particular, this tree, this Fn tree, can be considered as a canonical decomposition of the free group. And this canonical decomposition is well adapted to the automorphism that we are studying, because it is preserved by the centralizer of the element. So before the break, I just want to mention some historical remarks. So some few cases were already known. One is due to Bezvina, Payne, and Handel. They described a completely chaotic case. They describe the case where phi does not preserve the conjugacy class of any free factor. Any free factor. And in fact, they show something stronger. They show that the centralizer of phi is, as a finite index subgroup, up to finite index, it is isomorphic to an infinite cyclic group. And another case was known. It was due to Cohen and Lustig. They studied canonical decomposition for so-called twist automorphisms. These are automorphisms of the form. So if you take an alphabet x1 up to xn, so you look at the automorphism, which sends each xi to itself if I is strictly less than n, and it will send xn to xng, where g is an element of the group generated by the first n-1 letters. And they describe, in that case, a tree, an appropriate tree. So I will stop here for the first part of my talk. Thank you very much for your attention.